The aircraft's fuel system, specifically the Darwinian evolution of its valves, vents, and pressure seals, reads like a forensic case file of failures that almost happened and the few that did. And the place where that history is most visibly encoded is something you've stared at 100 times without realizing it. Look at the leading edge of the wing right next to the number 1 engine. Just behind the intake cowl, there's a flat rectangular panel about the size of a hardcover book, secured by a ring of fasteners. It's flush with the wing surface, painted the same color as the rest of the airframe, and utterly unremarkable. On most modern jets, that panel covers the fuel crossfeed valve, a mechanical junction that connects the left and right wing fuel tank systems, allowing fuel to be moved from one side of the aircraft to the other in flight. And here's where the layer of deception begins. The panel looks like a simple maintenance hatch. It is anything but. Behind that flat aluminum skin lies a motor-driven ball valve that can be opened or closed from the cockpit via a guarded switch on the overhead panel. When the valve is open, fuel from the number 1 main tank can flow through a titanium tube running the length of the wing, across the fuselage, through the center wing box, and into the number 2 main tank, or the reverse. But the valve itself is only one small part of a vastly more sophisticated system that spans the entire fuel architecture. The reason the cross-feed valve sits on the wing leading edge instead of somewhere more protected is purely historical. In the early days of swept-wing jet aircraft, engineers learned the hard way that fuel lines passing through the fuselage center section were vulnerable to battle damage in military jets and to fatigue cracking in commercial airliners. The classic example is again the de Havilland Comet, whose fuel pipes had to cross the pressurized cabin at specific points. The Comet's square fuselage cutouts for those pipes created stress risers that contributed to the structural failure of the aircraft. After the Comet's grounding, aircraft manufacturers began routing fuel lines through the wing structure itself, away from the high-pressure passenger compartment. The cross-feed valve moved out onto the wing. Now, here's the detail most passengers never consider. The cross-feed valve is always closed during takeoff and landing. It's opened only in cruise or during emergencies. Imagine you're at 40,000 feet and a leak develops in the number 1 tank. A bird strike, a crack, a faulty fuel cap seal. The left tank gauge starts dropping faster than the right. In that moment, the pilot can reach up and flip the crossfeed switch. The valve opens and fuel from the right tank can gravity feed or be pumped into the left engine, keeping it running. But if the valve were already open when the leak happened, the leak would drain both tanks, starving both engines. The valve must be closed by default. This is not a random setting. It is a rule written into the failure mode analysis of every jet transport designed since the mid-1960s. But wait, you've now discovered the crossfeed valve. You've decoded one panel on the wing. What about the others? What about the 3-inch wide panel near the wingtip, the one that looks like a small aerodynamic fence? That panel is the fuel vent system's NACA duct intake, a precisely smoothed air inlet that looks like a flat scoop carved into the upper wing surface. It feeds air into the fuel tanks to equalize pressure as fuel is burned. The vent is designed to operate at any angle of attack, even at 0 airspeed. But the real genius is what happens if the vent ices over. The engine's bleed air system can be routed backward through a check valve to melt the ice before the pressure differential collapses the wing tanks. And then there's the one you can't see at all, the fuel jettison nozzle. On wide-body aircraft, there's a small retractable tube that extends from the trailing edge of the wing, near the outboard flap track. If the aircraft must land immediately after takeoff at a weight exceeding its maximum landing weight, The flight crew can open a switch on the overhead panel, and fuel is pumped out through that nozzle, atomized by a high-pressure airstream and dispersed behind the aircraft. The fuel evaporates before it reaches the ground. But the nozzle itself is a masterpiece of fail-safe logic. It cannot be opened unless the landing gear is down, preventing accidental fuel dumping during cruise. And the system is designed so that the nozzle must physically extend into the airflow before the fuel pump can activate. A mechanical interlock that overrides any software failure. The cross-feed valve panel, the NAC vent, the jettison nozzle. These are the components of the fuel system that actually touch the outside world. But the inner architecture is where the true engineering obsession lives. And that obsession is what makes these systems so fascinating. Every mechanical interlock and failsafe you just saw exists because lives depend on a single valve not failing. If you want to keep uncovering the hidden logic behind what you see every time you fly, subscribe to join us on this descent into the aircraft's actual skeleton. Before we go deeper into the tank architecture, tell me in the comments, which failsafe caught you off guard? The vent ice protection or the jettison nozzle's mechanical override? You need to understand the tank layout. On a typical narrow-body aircraft like the Boeing 737 or Airbus A320, the main fuel is stored in the wings inside what are called integral tanks. Integral means the wing structure itself is the fuel tank. The skin, the spars, and the ribs form the container. There is no separate bladder. The metal is sealed with a special polysulfide sealant called PR1422, which is applied by hand between every joint inside the wing box. The sealant dries to a hard, flexible rubber that expands and contracts with temperature changes and wing flex without cracking. If a single rivet leak appears, the entire wing section must be drained, dried, and resealed, a process that can take 3 days. This is not trivial. The wing leak is the most common non-critical maintenance event that forces an aircraft into an unscheduled heavy check. The fuel inside these tanks is delivered to the engines by 2 independent systems. The primary system uses a set of booster pumps located at the bottom of each tank. These are electric centrifugal pumps that push fuel at a low pressure, around 40 to 60 pounds per square inch, to the engine-driven fuel pumps, which then bring it up to the 1,000+ psi needed for combustion. The booster pumps are redundant. There are 2 per tank, and each can supply the full required flow to its respective engine. If one fails, the other simply runs longer. But if both booster pumps in a single tank fail, the engine can still receive fuel through what's called suction feed. As long as the aircraft is below a certain altitude, typically 25,000 feet, the engine-driven pumps can pull fuel directly from the tank without booster assistance. The pilot must open a bypass valve called the suction fade valve to enable this. It's another case of a system designed not to work perfectly, but to work sufficiently under the worst plausible failure. The second fuel delivery system is the crossfeed itself. But crossfeed isn't just for emergencies. It's used every single flight for fuel balancing. In cruise, the flight management computer monitors fuel quantity in each tank, and to keep the aircraft's center of gravity within limits for optimal fuel efficiency, it automatically opens the crossfeed valves for short periods to move fuel from one side to the other. This is happening on your flight right now, at this very moment, if you're reading this at 38,000 feet. The computer is making micro adjustments, opening and closing valves, nudging fuel masses over the spars, while the passenger in seat 23A watches a movie entirely unaware. And here's where the title's first promise is directly fulfilled. You asked, how does jet fuel get from the ground to 40,000 feet without spilling a drop? The answer is a cascade of engineering decisions encoded into every component you've just read about. But the last link in that chain is the one you never hear about: the refueling panel itself. Next time you board, look for a small flush door on the underside of the wing, usually near the inboard end of the flap track, close to the fuselage. That panel is the refueling coupling access. It houses a single large diameter fitting, usually 2.5 to 3 inches in diameter, that connects to the fuel truck's hose. The fuel truck's nozzle locks onto this coupling with a quarter-turn mechanism. When the locking ring engages, it pushes open a spring-loaded poppet valve inside the aircraft's fuel line. The poppet valve stays closed when the nozzle is disconnected, sealing the fuel system against leaks and contamination. The key detail: the poppet valve is calibrated to close with a force of approximately 120 pounds. This ensures that even if the fuel truck's hose is ripped away by a tug, a real-world scenario, the valve slams shut before a single drop of fuel escapes the aircraft. The FAA requires that this valve close within 1/10 of a second of the nozzle's disconnection. But what about fuel expansion? An aircraft parked in the sun at 36 degrees Celsius at Dubai International Airport has fuel that expands significantly inside the sealed tanks. If the tanks were completely full, the expanding fuel would rupture the wing skin. So the fuelers always leave a 2 to 3% air gap, called the ullage, in each tank. The ullage space is connected to the vent system, which lets air in and out as fuel expands and contracts. But the vent system is also connected to the surge tanks at the wingtips. If a tank is overfilled, which is rare because the refueling panel displays the exact quantity in gallons, the excess fuel flows into the surge tank, which is empty during normal operation. The surge tank has a separate drain that allows fuel to flow out over the wing surface. This drain is designed to open at a specific pressure, acting as a last resort safety valve. If you overfill, the fuel doesn't spill on the tarmac immediately. It pools inside the surge tank, then exits through a small tube that runs along the top of the wing to the trailing edge. The pilot sees the fuel quantity discrepancy on the synoptic display, identifies the overfill, and orders the fuelers to drain the surge tank via a separate drain valve on the leading edge. But the important point is that the aircraft's fuel system has a built-in mechanism to prevent catastrophic overpressure without spilling fuel on the ground. But the story doesn't end at the wing. You've seen the tanks, the valves, the pumps, the refueling coupling, the surge tanks. You know how the fuel stays in the wings during cruise, how it balances side to side, how it gets to the engines. But there's a different kind of journey that the fuel takes. A journey inside the engine itself, where the chemistry and the metallurgy meet. The fuel, when it leaves the low-pressure booster pump, travels through a filter, then through a fuel oil heat exchanger. This is a device that heats the fuel using the engine's hot lubricating oil. Why would you heat the fuel? Because Jet A1 has a freezing point of minus 47 degrees Celsius. At 42,000 feet, the ambient temperature is typically around minus 57 degrees Celsius. The fuel inside the wing tanks is separated from that air by only a thin layer of aluminum. Without heating, the fuel would freeze into a waxy sludge, blocking the lines and starving the engine. The fuel oil heat exchanger raises the fuel temperature above the freezing point to ensure flow. The hot oil, in turn, is cooled by the fuel, returning to the engine at a temperature that keeps the bearings and gears within their operating limits. The two fluids exchange energy through a honeycomb of stainless steel tubes, separated by O-ring seals with a pressure delta of over 500 pounds per square inch. If those seals fail, fuel enters the oil system, or vice versa. The engine would stop within minutes. The seals are designed with a double barrier, a primary seal and a weep hole that drains any leakage overboard before it can reach the secondary flow path. That single double barrier and its weep hole, that's the kind of detail that separates a casual understanding from a real one. If you want to keep peeling back these layers, subscribe so you're here when we uncover the next hidden system. And before we move on, drop a comment with your reaction to the fact that a seal failure between fuel and oil can stop an engine in minutes. Leave a word or a thought. But wait, you're 3/4 of the way through the journey and you haven't yet answered the final question the title demands. You know how the fuel gets to the engine. You know how the tanks prevent spills on the ground and at altitude. You know the crossfeed, the boost pumps, the heat exchanger. But what happens when you need to keep the engine running after a catastrophic failure? A bird strike to the wing that opens the fuel tank to the atmosphere? Or a fuel leak in the dry bay? The answer lies in the engine's own last-ditch fuel system, the ejector pump. Inside the engine's fuel control unit, there is a small venturi, a narrow tube shaped like an hourglass. High-pressure fuel from the engine-driven pump is forced through the venturi, creating a vacuum at the center. That vacuum draws fuel from a separate pickup line that sits at the lowest point of the fuel tank, called the sump. The sump is what catches any water that might have condensed inside the tank, because water is heavier than jet fuel and sinks to the bottom. The ejector pump is designed to pull fuel from the sump, fuel that was otherwise considered unusable because of the risk of water contamination. But in a firefight, that sump fuel is all that remains. The ejector pump can extract the last few gallons from the sump, water and all, and push it through the fuel nozzles into the combustion chamber. The engine will run on that mixture. It will run rough, it will run hot, but it will run. And that's what the engineers designed. Not an elegant solution, a last resort solution. Now you know the full chain. From the fuel truck's nozzle to the ejector pump's sump pickup, every component shares the same design philosophy. Anticipate the failure, build the escape route before the failure happens, and hide the escape route so well that nobody except the troubleshooting engineer ever needs to think about it. But you're now the exception. You see the black nose. You know the vent duct. You've decoded the fuel system. So as the ground crew finishes refueling and the driver sets the parking brake for the next truck rotation, think about the last component that makes this all work. The valve that never moves. The refueling coupling's poppet valve, sitting closed under 120 pounds of spring force, waiting for the next connection. That spring was designed 20 years ago, forged in a factory in Sheffield, England, heat-treated to 60,000 cycles. It will close fully for the entire lifetime of the aircraft, 30 years, 40,000 flights, without ever being replaced. Because if it ever failed to close, the fuel would spill. And the engineers who designed it knew that someone would be depending on it at 38,000 feet on a dark night with no backup. So they made it fail-safe. They made it invisible. And they trusted that you would never need to know it existed. But now you do. And that's exactly what this channel is about. But now you do. And that understanding doesn't just apply to the refueling panel or the crossfeed valve or the ejector pump. It applies to every fuel-related component you'll see from the moment you step onto the jet bridge. Next time you board, Glance at the underside of the wing as you cross the tarmac. Spot that refueling panel. Remember the 120-pound spring and the 1/10 of a second closure time. Then look at the wingtip itself. You've likely noticed the small upward-angled metal tube sticking out from the trailing edge of the wingtip. It's about the diameter of a garden hose, pointed backward. On most modern airliners, that's the fuel vent mast. Its sole purpose is to expel any excess pressure or overflow from the fuel tanks into the airstream, where it is atomized and dispersed. But the vent mast is not a simple open pipe. Inside, it contains a complex flame arrestor screen, a honeycomb of fine metal mesh that prevents a lightning strike on the wingtip from propagating a flame front back into the fuel tank. The mesh dissipates the electrical energy and quenches any potential ignition before it reaches the vent system's internal plumbing. The FAA mandates that the flame arrestor screen survive a direct lightning attachment without melting through, a test that involves a simulated strike of 200,000 amperes. And that vent mast is connected to the surge tank you already know about. If the surge tank overflows, the excess fuel travels up that tube and exits into the slipstream, where it immediately evaporates in the high-speed airflow. You will never see a fuel spill on the runway from a properly operating vent mast. The fuel is gone before it reaches the ground. But there's a second function the vent mast serves that most engineers never mention. It also equalizes the pressure inside the fuel tanks during rapid altitude changes. When the aircraft descends from cruise altitude to landing, the external air pressure rises dramatically. The vent mast allows outside air to enter the tanks through the same flame arrestor screen, preventing a vacuum from forming that could collapse the wing structure. On a hard descent into, say, London Heathrow, that vent mast is handling nearly 1,000 cubic feet of air per minute, moving in and out as the aircraft breathes. And yet, for all that engineering, the fuel system still has a vulnerability that every pilot knows and every passenger should respect. It's called the center of gravity shift. The fuel in the wings is distributed precisely to keep the aircraft balanced in flight. The fuel is stored in multiple tanks: the main tank, the center tank, if the aircraft has one, and the surge tanks. During takeoff, the center tank is usually full to shift the center of gravity forward for stability. As fuel burns off, the center tank empties first, moving the center of gravity aft. The flight management computer actively manages this transition, pumping fuel out of the center tank and into the wing tanks at a carefully calculated rate. If the computer failed, or if the pilot mismanaged the fuel schedule, the center of gravity could shift far enough aft to make the aircraft uncontrollable, a scenario called tailplane stall. This has happened in real-world accidents. In 1999, a Egyptair Boeing 767 crashed into the Atlantic Ocean after the crew mismanaged the fuel system, allowing the center of gravity to shift beyond the aircraft's design limits. The NTSB investigation concluded that the crew likely failed to monitor the fuel quantity and didn't activate the crossfeed valves to correct the imbalance. Now, you might think this is a rare event, a consequence of pilot error rather than engineering failure. And in that specific accident, that analysis is correct. But the engineers who designed the fuel system also designed it to be resistant to pilot error. The crossfeed valves can be activated automatically by the flight management computer in any modern aircraft. On the Airbus A350, the entire fuel management process is automated. The computer decides when to open the crossfeed, when to pump fuel from the center tank, and when to shut it off. The pilot needs only to monitor the fuel quantity on the synoptic display. If the computer detects an imbalance of more than 1,000 pounds between the left and right wings, it automatically opens the crossfeed valve to correct the imbalance within seconds. This automated system is what makes the airplane survivable in the hands of a distracted crew. And there is one more detail you need to understand before you land. The fuel system's final layer of protection is the ignition source isolation. Inside the fuel tanks, the airspace above the liquid fuel, the ullage, is filled with fuel vapor mixed with air. In a properly operating system, the vapor-to-air ratio is too lean to ignite. But if the aircraft climbs rapidly and the pressure in the tank drops, the vapor can condense, creating a rich mixture that is combustible. To prevent a spark from igniting this mixture, every electrical component inside the fuel tank, the booster pump motors, the fuel quantity probes, the level sensors, is either explosion-proof or submerged in fuel. Explosion-proof means that the component is sealed so tightly that an internal spark cannot escape the casing. Submerged means that the component operates below the fuel level, where the liquid itself quenches any potential arc. The fuel quantity probes, which are essentially metal rods that measure capacitance between the rod and the tank wall, are also designed with a secondary seal that isolates the electrical connector from the fuel vapor if the primary seal fails. So next time you see a fuel truck hook up to the wing, understand that the entire process, from the quarter-turn coupling to the 120-pound spring to the flame arrestor screen to the explosion-proof booster pump, is designed around the principle of fuel containment at all costs. One single drop of fuel spilled onto a hot engine exhaust is all it takes to start a fire on the tarmac. One single arc inside the tank is all it takes to explode an aircraft. The engineers have built a system that prevents both with redundant overlapping layers of protection. Those explosion-proof components submerged in fuel, operating silently behind a wall of engineering that most passengers will never see. That is the kind of hidden architecture this channel exists to decode. If you want to keep pulling back the layers on every system that protects you at altitude, subscribe and let the next reveal land in your feed. And if that fuel tank safety chain surprised you, drop the word explosion-proof in the comments, because now you know exactly why it's there. You walked onto that plane knowing one thing. Now you know the full story. And the next time the engine spools up and you feel the vibration through the fuselage, you'll know exactly how the fuel traveled from the ground to the combustion chamber without a single drop escaping. That's the system. That's the secret. But understanding the system isn't the same as seeing it. And the final piece of this puzzle isn't in the wing at all. It's in the cockpit, on a screen you'll never sit behind. Every modern airliner has a fuel synoptic page, a digital schematic that displays the entire fuel system in real time. On that page, you see the tanks as blue rectangles, the fuel quantity in pounds, the pump status as green or amber icons, and the valve positions as open or closed symbols. The crossfeed valve, the jettison nozzle, the booster pumps, they're all there, represented by simple lines and arrows. The flight crew uses this page to monitor the system, to diagnose faults, and to command the fuel transfer you now understand in detail. But there's a detail on that synoptic page that most pilots don't think about, and you've never seen. At the bottom right corner, there's a small readout labeled Fuel Temp. It displays the temperature of the fuel in the main tank in degrees Celsius. On a typical flight at cruise altitude, that temperature reads somewhere between -20 and -40 degrees Celsius, depending on the ambient air temperature, the flight duration, and the fuel burn rate. The pilot monitors this number because if the fuel temperature drops below -47 degrees Celsius, the fuel can begin to gel, forming wax crystals that clog the filters and block the fuel lines. Now, here's the silent engineering handshake. The aircraft's fuel system is designed to prevent the fuel temperature from ever reaching that gel point. The fuel oil heat exchanger you learned about earlier ensures that the fuel entering the engine is warm enough. But the fuel sitting in the wing tanks, far from the engine, is exposed to the same minus 57 degrees Celsius air that freezes the clouds. So how does the aircraft keep the fuel in the tanks from freezing? The answer is heat transfer from the fuselage itself. The fuel in the wing tanks is separated from the cabin air by only a thin layer of insulation and the aluminum skin. The cabin, pressurized to the equivalent of 8,000 feet, is kept at a comfortable 22 degrees Celsius. That heat conducts through the fuselage structure, through the wing spars, and into the fuel. It's not a fast process, but over the course of a long flight, it raises the fuel temperature by several degrees. The aircraft doesn't actively heat the fuel in the tanks. It relies on the thermal mass of the cabin, the passengers, and the structure itself to keep the fuel from freezing. And when that isn't enough, when the aircraft is flying over the North Atlantic at minus 60 degrees Celsius for 8 hours, the fuel system has one more trick. The aircraft can transfer fuel from the center tank, which is located inside the fuselage and is therefore warmer, into the wing tanks. This warmer fuel mixes with the colder fuel and raises the overall temperature of the wing tank fuel. The flight management computer can automatically initiate this transfer if the fuel temperature in the wing tanks approaches the gel point. It's a simple solution, born from a simple problem. The fuel is cold, and the only way to warm it is to move it. So now you see the full picture, from the refinery to the fuel truck, to the quarter-turn coupling, to the booster pump, to the fuel oil heat exchanger, to the combustion chamber, and back to the wing tank itself, where the fuel is kept warm by the bodies of the passengers sitting in seats 30 feet away. Every stage of the journey is monitored, regulated, and protected by a system that has been refined over 8 decades of flight. You walked onto this aircraft with a question. How does jet fuel get from the ground to 40,000 feet without spilling a drop? The answer is a symphony of mechanical precision, forensic history, and redundant design. The black nose of the radome, the cross-feed valve on the leading edge, the Nacker vent on the upper wing, the jettison nozzle at the trailing edge, the refueling coupling with its 120-pound spring, the flame arrestor screen in the vent mast, the explosion-proof booster pumps, the fuel oil heat exchanger, the ejector pump in the sump, and the silent thermal handshake between the cabin and the wing. The system works because it was designed to fail in controllable, predictable ways, and because the engineers who built it knew that someone, maybe you, would be depending on it at 38,000 feet on a dark night with no backup. So the next time you hear the click of the refueling panel closing, remember the spring. And when the engine spools up and the vibration settles into a steady hum, remember the fuel oil heat exchanger, keeping the fuel liquid and the oil cool. But mostly, remember this: you are not a passenger in a plane. You are a passenger in an engineering document with 1 million pages, written by people you will never meet, who designed every component to keep you safe without ever asking for your thanks. And that is the secret. Not the system itself, but the fact that you now see the system at all.